Welcome to the Snake video game tutorial in Python, part 4b. In the previous video, what we did was make some changes to our code that allowed us to add a tail to the program. We haven't actually added the tail to the program, but we came up with a plan for how the tail would grow using some squares here. I did a step-by-step demonstration of an idea to move the tail and to grow the tail. Then I made changes in the code that called the routines that would do the work of growing the tail and moving the tail, but I did not write the routines that would grow the tail and move the tail. So in this video, that's what I'll do. We will grow the tail and we will move the tail. So let's look back at our kind of high-level description of our algorithms here. So let's work with growing the tail first. We said that we were going to move the food once the snake collided with the food, and we already do that. And then we said we were going to grow the tail by adding a turtle exactly where the head of the snake is. And then we're going to move the snake head forward. Moving the snake head forward is also done. That means we only have to focus on growing the tail by adding a turtle exactly where the head is. All right. But we haven't really talked about what the tail is in our program, except for I mentioned that the tail would be turtles, similar to the head and similar to the food. The advantage of making the tail, constructing the tail of turtles is that the turtles have this built-in ability to check their distance from any other given turtle. And so eventually in this game, we would want to have a check to make sure that the head has not collided with the body of the snake. And so we want to use turtles to do that. But, okay, so we have not talked about where we're going to get all these turtles and how we're going to keep track of them. So the way we're going to keep track of a bunch of turtles that make up a tail is that we're going to put them together in something called a list in Python. Now, if you're in my class, you have already seen lists in passing. In this video, I'm not going to go into detail of what a list is or how to use it. I will have some explanation of how to use the lists in this way. There will be an additional video that I will give you a link to that will explain lists from a more basic perspective and possibly in more detail. And I refer you to that if the lists aspect of what I'm about to do is confusing. But I will try to explain as I go. Okay, so a list is a data type that allows you to collect a number of other things in a program in a way that they're lined up in a certain order. So, for example, those things are generally data. Today we'll be working with turtles as the things that are going to be in this list. So you can have a list of turtles. And the advantage of a list of turtles is we already have an order to the turtles that are supposed to form our tail. And we want to maintain that order. It's important that the turtles stay in order. So if we put them in a list, one after another, it will allow us to do something to them in order, because they'll be kept in the same order for the entirety of the program, or at least until we decide to change that. But in this program, we're going to keep them in the same order. So here's how you create a list. So I'm going to create a list called tail. And this part acts like any other variable. So the list is actually a variable. So tail equals open bracket, close bracket. You can see that Replit wants to close the brackets for me. Okay, so what did this do? So I have a variable called tail, and it is equal to a open bracket and a closed bracket, which represents the empty list. So currently we have a tail that has no length to it. We have no tail. Well, there's a difference between something not existing in terms of a list and something being empty. So what we have here is we do have a list, it just doesn't have any things in it. So it's something that will allow us to put things in it, but currently it's empty. It's just an empty container. And by creating the list but having it empty, it allows us to refer to the list in the program before there's anything in it. So, okay, so our tail is an empty list currently. How do we get things into that list? Well, when the program starts out, the tail has no turtles. There is no tail. It's just a snake head. But as soon as the turtle, that is the snake head, eats the food, we finally get our first segment to our tail. And then we have a tail of length 1 with one turtle in it. And that means we will have a list of length 1 as well. That is our tail. When it eats the food the second time, another turtle will be added. The list grows by 1. And we have a tail of length 2, and so on and so on. As the list gets longer and longer, it's collecting the turtles that form the tail. And on the screen, we will see more and more turtles being managed by that tail. All right, so how do we go from the tail being empty to the tail having its first turtle? Well, grow tail, if we look here for what we wrote for growing the tail, grow the tail by adding a turtle exactly where the head is. So this can be our first turtle. So it's fine that we start out with empty lists and then we add a turtle the first time to start our tail. The tail can remain empty until it's time to add that turtle. So let's create a function here, grow tail. So we're defining a function to grow the tail. Now, looking at the high-level description of our algorithm, it looks like growing the tail requires us to create a new turtle. So we could say turtle dot, oops. So this is how we've, turtle. So this is how we've made a turtle in the past, like this. But I have a different way that I'm going to make this turtle. I'm going to use the clone function. So the head of the snake is already a turtle, and it already has some settings that we want to keep for our tail segments. Like, for instance, that it's square, and that its speed has been set to 0. So, and that it's also in pen up mode. So we would like to copy the head and use the copy as the first segment of our tail. So to do that, to copy a turtle, you can use the clone function. So head.clone will create a clone of the head of the turtle. And temporarily, let's create a variable to hang on to that. Let's call it new segment for the segment of our tail. New segment equals head.clone. So we're going to clone the head of the snake, and we're going to take the clone of the head, and I'm going to place it into a variable called new segment. So now new segment is a turtle. That is a new segment for the tail. And so just like we did in our demonstration, I want the color of that to be a different color. So we'll make it light green. So we'll say new segment dot color equals light green, I think. And then, so now we've created a new segment. We've changed its color. And what we haven't done is we haven't put it into our list so that we can keep track of it. So our list is called tail. And one way to add things to a list is to insert them in a particular spot. So as we said in our description over here, that we would be putting the new tail segments right, well, we said we'd be putting them right where the head is. That's on the screen. That's the location on the screen. In the list, we want to place the new tail segment at the beginning of the tail, so right behind the head. So we're going to consider the beginning of the list to be the beginning of the tail. And so that would be position 0. Lists start at 0. Well, so items that are in a list each have a number that's associated with them. And you'll see that when we start using the array. I'm sorry, using the lists. So to insert this segment into our tail lists, we use the insert command. We say we're going to insert it at position 0. And what are we inserting into the tail list? We're inserting the new segment. So right now, the segment is inside the lists. And so the tail has grown by 1 there. And one of the benefits that we got out of cloning the head is the head, the new segment, also has the current position of the head. So the new segment will be exactly where the head is. So when we move the turtle forward, the new segment will be where the head was. And then you'll see the head and the tail. So I can't run this program yet because we have, well, I'll show you. We left this program in a state where it wouldn't run because we had 2 routines that weren't written. So if you have a routine, see, it says that move tail is not a defined function. So if I comment out move tail, now I can run the program. Bad input, line 71. So I can't leave this else empty, so I have to comment it out as well. Okay, so if we run this now, our program looks like this. And so we can go around and we can test to see if a new segment is created. And it is. It's created. Whenever we run into the food, a new segment is created. And those new segments have been added to the list. So the tail now is made up of these. You can see 5 segments on the screen. But you might say, well, wait a minute, you said that they needed to be in order and they needed to be kept in order. Well, they are kept in order in the list, but on the screen, they have the positions where the head was when we added the segments to the list. The thing that's missing, the thing that keeps them looking like a tail, will be this move tail function, because that will move each segment along behind the head as the head moves. Right now what's happening is the turtles are being placed in the play space, but then the head is moving forward and the tail never moves. So you've got the stationary pieces of the tail just scattered all over the game board. But what we verified is that we have created successfully several new pieces to our snake tail. We can't really see whether they're in order or whether that kind of works or makes sense, because as they're scattered all over the place, they don't look like a tail. But moving tail would solve that problem. So just to show what this looks like, if we start out with the snake head and the food, when the snake head hits the food, the food is transported somewhere else. A tail segment is created there, and because the tail is never moved, the head moves on until it hits the food again. Then the same thing happens. The tail segment is created, the food is moved, or I should say the food is moved first, tail segment is created, the head moves on. So that's what's happening in our program right now with those pieces. Okay, so now we need to do something to make the tail look like a tail by allowing it to move when the head moves. Okay, so here's our grow tail function. Let's, after it, create a move tail function. So you notice that I like to, so even though our program wouldn't run because we hadn't written move tail yet, I like to comment these things out and then test if the code I've got runs. And even though the program isn't complete, you should understand, or you should know what your program should be doing at every point, along you writing it. So that allows you to be able to test to see if the program meets your expectations, even though it's not complete. So I knew that this is what was going to happen with my snake parts. So just to make sure that my code was working right, I went ahead and commented out the parts that weren't that were calls to things that weren't written, and made sure that that the program met my expectations. If, for example, the program had not met my expectations, then one of two things would have been true. Either I was incorrect about my expectations, which is possible, or there was something wrong with the code that I wrote. So then I would need to figure out, was my expectation wrong? And that's part of what having these manipulatives over here, these digital manipulatives, was for. If I walk through what I expect to happen over here and it makes sense, then I know that my expectation makes sense. So then, once I'm convinced that my expectation made sense, because I've stepped through it, I've gone through it step by step, and there's nothing missing, then if my code is then wrong, then I have to look at the code I wrote and see, why doesn't the code do what I expected it to do. So that's an important debugging series of steps that you go through to reassure yourself that what you expect is correct. Okay, so on to move tail, back to move tail. All right, in order to move the tail, we said that starting at the last piece, for every turtle that makes up the tail, move a tail piece to where the piece in front of it is. Okay, this is important. We found out that you have to do it in reverse order. You have to start at the end of the tail, not the beginning, because you're making use of the current position of the segment in front of whatever segment you're talking about. And so you need to start moving from the back so that the segment in front still is available to you. All right. So this is where it's important that we're using a list, and features of a list become useful. So a feature of a list is that here is our list called tail. Right. So our list, the variable which contains our list, is called tail. And one of the things that makes a list is that you can do what's called indexing into the list, which means each of the pieces, each of the things that's in the list now has a number which you can use to get back that thing. For instance, if we only have one thing in this list, then the number associated with that thing is going to be 0. So the 0th thing in that list is going to be called tail, open bracket, 0, close bracket. It was called new segment up here when it was created, but once it was put into the list, then you could access it by talking about tail, and some people would pronounce this tail sub 0. So that's actually easier than saying tail, open bracket, 0, close bracket. Tail sub 0. So this is tail sub 0 would be the first segment in the tail. Tail sub 1 is the second segment in the tail. Tail sub 2 is the third segment in the tail. So this makes it really easy to write programming code that, instead of referring to a single item, can do something to each member item of a list. And that is exactly what we're going to do, because if you looked at the description of our algorithm here, we're doing something to every piece in this list. So how do we do something to everything in the list? If you recall your repetition structures, we have the ability to make a loop that counts for us, and we can have it create a number that can be used to index into every that could be used to index into this list, giving us access one at a time to every item in this list. So we're going to use a classic loop name for a loop variable, I. So when we say for I in range, and you should have already seen this the syntax in my class before. This is loop syntax for for loops, and the range call, which will generate it actually generates a list of numbers. So if we say for I in range 0, 10, this will give us the numbers from 0 to 9. So it will give us 10 things. It will create a list of 10 numbers. And as the for loop repeats, first I will take the value of 0, then I will take the value of 1, then 2, then 3, then 4, then 5, all the way through up to 9. So it will go 10 times. It's always 1 before you get to the number that's here. So that's how we would count up to 10, at least count up 10 things starting at 0. And we know that the list also starts at 0. So how would we count up to the entire length of the list? Well, there's another new call, or another call I haven't talked about before, called len, that gives you the length of a list. So if the length of a list is 5, len will return 5. And to get the length, you pass in the name of the list, so tail. So len tail will give me the length of the tail. So if tail is 5, this will go from 0 to 4, because it's always 1 before the actual value here. So from 0 to 4, that would give me the 5 items in my list. The 0th item, the first item, second item, third item, fourth item. That's actually 5 items. 0, 1, 2, 3, 4, 5. Okay, but note what we said, that we actually wanted to start at the last piece and go backwards. So the last piece, the last item in a list, is the length of the list minus 1. Think about that for a second. Let's say there are 3 things in the list. They would be called tail sub 1, tail sub 0, tail sub 1, and tail sub 2. So if the length is 3, tail sub 2 is the last thing in the list. So we have to use length of the tail minus 1. We want to go all the way down to 0. So as I noted before, it always stops 1 before the number that's here. So if we're going down to 0, then we want it to stop when it gets to -1. That way it includes 0 in this backwards count. And then the last parameter of the function range will tell us how we go about counting. So for instance, if we count by 2s, it'll only do every other number. If we count by 3s, it'll do every third number. But we can also put a negative number in here to go backwards. So we want to count by negative ones. All right, so going through this again, if tail has 3 items, 0, 1, and 2, we start at length of tail minus 1. That would start at 2. We'd go until just before we get to negative 1, and we start count by negative 1. So we start at 2, then we go backwards 1, then that goes down to 1, then we go back down by 1, and then that would go to 0. And then when it got to negative 1, it would stop. So it wouldn't do this. It wouldn't go back into this loop for negative 1. So if we say tail I now, if we talk about tail sub I is going to be every item in the list one at a time in this loop, starting with the last item and working backwards. So what do we want to do with tail sub I? Well, we want tail sub I to move, and that's what the goTo function on the turtles does. We want tail sub I's turtle to go to some x, y location, and that x, y location is going to come from the turtle, the turtle that's in front of it. It's going to come from the segment that's in front of it. So what we can do is talk about, since we know that tail I is the current tail, then what would be the item that's in front of it? So if for tail sub 5, let's say, the segment in front of it, because we said the front of the tail, remember we said the front of the tail was 0. So tail sub 5 is some segment in this tail. What is the one that's in front of it? Well, tail sub 4. So for any segment, the segment that's in front of it is tail sub whatever minus 1. So if we refer to tail sub I, that's the current segment, but tail sub I minus 1 is the segment that's just in front of this. And if we want to get the x coordinate of that, it's .xcor. That's the call. It's a function called xcor to get the x coordinate. For the y, it's exactly the same thing, but with y coordinate. So tail sub I minus 1 dot ycor. So now, for eigenrange of length tail, oops, didn't close that off. And I also made another error because I did not do this. Okay. And I don't know why this is here. That's a mistake. Okay. So range from, length tail minus 1, 2 minus 1, going backwards by 1. Okay. So just verifying what I did there. Okay. So now we've moved each tail segment to the segment that's in front of it. So let's see what happens when we run that. Something is wrong. What happened? So we missed something that we had in our algorithm, but we haven't actually done. And it looks like tail segments are disappearing. Can we tell by looking at it? I stopped disappearing. Okay, in our algorithm, we said that when you get to the frontmost piece of the tail, move that piece to where the head is. And we didn't do that. Right. So we went through our loop and we did not ever reference the head. So we didn't, we're not moving the frontmost segment. Because we want the zeroth tail segment to be treated differently. But no matter what we do, well, let's see. We want the zeroth tail segment to be treated differently. So that means we need an if statement. So if I equals 0, then we want to do something and else. So if I isn't 0, we already know this is what we do. But if I is 0, then we want tail I, which is actually tail sub 0, to go to the x coordinate of the head and the y coordinate of the head. So by not moving the segment that's right behind the head along with the head, then we never move the tail along, so it never connects itself. So it's kind of funny to think that this is actually the thing that keeps the whole tail connected. Well, I guess we should test it out before we say that for sure. So let me run the program again. Oops, I have an error. Probably a syntax error. Line 120. Oh, I didn't put a colon after else. It happens. Okay, so here's our game. Let's go. So I was correct. So that is what actually keeps the tail together. It is the fact that we always move the first tail segment along with the head of the snake, at least in this way of doing things. So to be honest, this whole program could be written differently. I mean, there's a lot of different ways you could write a snake program in Python. This is just one way. So now that we've gotten this far, this game is almost playable. So the things that are missing, I can count on 2 fingers. One, even though it's keeping track of a score, it doesn't display the score. The score is also kind of boring because it only goes up by 1. We were previously printing it to the console here. And the other thing it doesn't have is, notice I can run into the snake body and there are no consequences. So it doesn't have the consequence that as your snake gets longer, it actually gets a lot harder to play the game. It's actually a game right now that doesn't get any harder. You just actually have fun, I guess, seeing the snake get larger. And that does not make the game harder because you don't have to avoid the snake body. So those are 2 things that right now I'm going to leave you to think about. Well, I would say that because this is the 4th video in this series, and it is also the close to the end of the school year, there may not be a 5th video in this series. If you're trying to improve this game, the 2 things that I think you should try to solve are getting the score displayed on the play space. I would actually also suggest you increase the play space because it's kind of small the way it is. It'd be a much more interesting game if the play space is larger. And solving the problem of having the head collide with the body and having that end the game. I may make a video in the near future that will show you the solution to those 2 features. And if I do, I will post it to a playlist that this video already belongs to, and I will post it to my YouTube channel. So if you watch the YouTube channel or watch the playlist, or you watch the remote learning website where I've been posting projects, it will be announced in all of those places. So if you are interested in seeing the solution to that problem, it may not show up for a couple of weeks. It depends on other work that needs to get done, but watch those spaces if you want to see the solution to those features. But I urge you to actually try and implement those features yourself if you've been enjoying playing with this problem. Thanks for watching.